we are introducing the concept of stationarity. Quite often, we have a random process, x of t, and based on the past history of x of t, we collect some data and we want to use it right now or in future and so on. So that means that some statistics of this random process should be constant, should not be different in the past and now. So we call these stationarity. And if this property does not exist on your random process, you cannot make this application. So what is a stationary process? There are different ways you can define a random process, a stationary, and it has different senses. We say a random process is a stationary in some sense, and in the sense of one specific statistic. If that statistic is invariant to a time shift. Now, this is a very wide, general, and important definition, but let us have one example. We say that a random process is a strictly sense stationary or a strict sense stationary if all statistics of x of t and x of t plus 2 are equal. That means that if you make any delay, all statistics, they remain unchanged. This definition is very strict and it should be applicable to all statistics. And because in lots of applications, some of the statistics are not changing with time, some others they change, the strict sense stationary is quite often just theoretical. So if a random process is strictly sense stationary, then the joint distribution of some samples, because the joint distribution is a statistic of your random vector, should be equal to the joint distribution of the delayed version of that. So I take these samples at time t1, t2, let's say t3, etc., and tn, so some arbitrary time samples, and I delay these ones, these time samples, and I take another set of samples at time t1 plus 2, t2 plus 2. I shift all these time instances with amount of 2, and let's say this tn, this distance is also 2, and I take new set of samples. So I will have two random vectors, this one and this one. So if the joint distribution of this one and this one are equal for all 2 and for all t1, all t2, etc., for all n and for all tn. Okay, then we say that this random process is a strictly sense stationary. So remember that this definition is same as this one. So this one means that this definition means that the joint distribution of this random process when the samples are taken at t1 to tn is equal to the joint distribution of the samples at time t1 plus 2 tn. So you just make a time delay and you don't see any change in the joint distribution. In that case, you call it a strictly sense stationary. I repeat again, this definition is too strict, and as a result, because you need all the distribution to be time invariant, and this is not the case for many random processes, so you need less restrictive definitions as well. And again, I repeat, this should be valid for all n and for all time instances. We say that a complex random process which is equal to the real part plus j imaginary part is stationary if x and t and y and t are jointly stationary. So it's jointly stationarity is also. So to make it less restrictive, we could define first order stationarity. That means that the PDF of one sample is not changing with time. So that means that this distribution, this PDF at time t is equal to the PDF at time t plus 2, because here I made a time delay of 2 and the distribution is not changed. So therefore, this should not be a function of 2. So it's kind of like a constant function. It's a function which is not. So, but if it is not first order stationary, this PDF will be a function of t. we say that a random process is second order stationary if the joint distribution of two samples is equal to the joint distribution of two samples when this one and this one have a time delay too, and this one has a time delay. So in that case, the joint distribution is only a function of the time difference, because this should be true for all two, all T1 and all T2. So what I could do, I could replace 2 is equal to minus T1. So if I do that, so this will be joint distribution of x of t minus T1, T2 minus T1, and this one becomes 0. So one of the variables will disappear. So the first order stationarity, second order stationarity, strictly sensitive stationarity, these are definitions. But even these cases may be too restrictive for some application in which you don't have the distribution at all. This is why we need to define another definition of stationarity which is a little bit wider.